If you take the example of graphite, graphite is like a deck of cards, and when you charge your battery, lithium ions go from the cathode into the deck of cards.
Welcome to Nano Matters, the podcast that explores examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Here with me today is Rama Podila, Assistant Professor of Physics and Astronomy at Clemson University. So Rama, a lot of your research is at the intersection of physics and health, but you also have projects that are focused on energy generation and storage. What interested you in energy research?
The main thing that interested me was, there's a lot going on with global warming and climate change. And so there is definitely a great need for coming up with new ways to generate energy that require less carbon dioxide emissions, and as well as coming up with new electric vehicles that can offset emissions from gasoline vehicles. So this was what got us interested in energy storage and energy generation, mainly to fight climate change.
So I understand that some of your work has application in space, like maybe in spacesuits themselves or in a rover that would be used on Mars. Could you talk to the challenges of developing and designing batteries for these types of applications?
I love the movie Martian, and if you read the book or watch the movie, you would see that there are a lot of technologies that are featured in there, like thermoelectrics or other battery technologies that are also useful for fighting climate change and global warming. And one of those is batteries. So they have similar challenges for electric vehicles. That is, we want to reduce the weight of the battery itself, that we want to pack more energy into batteries and be able to deliver it very quickly so that batteries can truly replace gasoline. And in terms of space applications, when something is taking off and you want to have as low weight as possible on the vehicle, so it's important to make batteries that are highly efficient. They can store a lot more energy in less mass, in less volume. And in terms of spacesuits, when astronauts go out to perform these extravehicular activities, they wear these EVA suits, which have batteries that ensure that everything is going on, that the suit is powered. And so these batteries, if they are very heavy, it's very uncomfortable. Not because in space there is no gravity really, but in terms of taking off and in terms of maneuvering, it's not a weight problem that the astronaut is weighed down by these batteries, but it's more of making the suits comfortable enough for operation and for making sure that a lot more energy is packed into the suit. So that was the challenge for spacesuits. So we were working on increasing energy and power density for those spacesuit applications. And in terms of rovers, the temperature range the rovers would be exposed to in space is different. So we need to come up with new electrolytes. The electrolytes that we have in today's batteries are not directly suitable for space applications. So we were trying to come up with new electrolyte systems that have a wider temperature range and that could be used in space.
So when you're talking about these applications in space and the challenges that you just outlined, how does nanotechnology play a role in helping you solve those issues?
That's a very good question, Lisa. And as you know, these nanomaterials have a very high surface area because you're grinding the material into smaller parts. So they have much higher surface area, which makes them more efficient for energy storage because the more surface area, you can store more charge. And that's one of the ideal things about nanomaterials. And another thing is today's lithium-ion batteries use graphite or LTO or some other material as an anode in a lithium-ion battery. If you take the example of graphite is like a deck of cards. And when you charge your battery, lithium ions go from the cathode into the deck of cards, and they're stored in the deck of cards, which is graphite. And then when you discharge, the ions are released, and that's how you power the device. But this graphite has a theoretical limitation. It can only store so much charge per gram material. And by increasing the surface area, we can definitely increase this charge, but it is still limited by the nature of carbon in this graphite. The other alternative is to use silicon. Silicon can store much, much higher charge compared to graphite, at least 2 to 3 times more. So you can reduce the weight, that is, you can pack more energy per gram of material if you use silicon. But the problem with silicon is that when lithium ions go into silicon, it just expands and then it bursts open, and then the entire material gets pulverized, which is a big problem for having stable batteries. So what we did was we used a combination of carbon nanotubes and silicon nanoparticles to come up with an anode architecture in such a way that this pulverization of silicon is no more a problem, and that we can have long life cycles up to 1,000, 2,000 cycles. So these batteries can not only pack so much power, but they're stable, because now these carbon nanotubes are interlinked between small silicon nanoparticles. So even if they are pulverized, they still fall back within this foam of carbon nanotubes, and they're still electrically connected. And that's how we use nanotechnology to address the challenge with silicon anode, to pack more energy into per gram of material.
I understand that you have done some work in triboelectricity. Can you talk about what that is and how it could be used?
So most people, when they're studying introductory physics, they're taught this glass rod and silk cloth experiment. When you rub a silk cloth on a glass rod or a comb through your hair, and then it attracts small pieces of paper. This is a triboelectric effect. That is, you're generating charges by applying some sort of a mechanical force. So if we can convert mechanical energy into charges, then we should be able to also convert mechanical energy into usable electricity. And that was the whole idea of these triboelectric nanogenerators, where we can generate more charge because nanomaterials have higher surface area. So when you rub two materials together, the higher the surface area of each material, higher the charge you would produce, because at the microscopic level, more of the material is in contact if the materials have higher surface area. So more parts of the materials are in contact with each other. So we produce more charge. And so these cannot produce very high currents. They produce high voltages, but they produce very little current. So their power is still limited, but they have enough power for microelectronics. For example, you don't need so much power, let's say, to power your calculator, or not so much power to power your phone, or some other microscopic things that we use daily. And so our goal was to see if we could use these triboelectric nanogenerators for powering micro devices initially. But then later we realized that, if we could choose the right materials, like we could make some materials like graphene and Teflon, or some sort of highly electronegative material, we could harvest the mechanical energy even from ocean waves. So there's a lot of mechanical energy in ocean waves. So by choosing the right pair of materials, we could harvest all that energy. And this is majorly led by Professor Ziel Wang at Georgia Tech, but we got into that recently. And along those lines, we have come up with some new materials that can enable not only mechanical energy conversion to electricity, but they have enough high voltage to create a significant electric field to wirelessly transmit this energy directly into capacitors or batteries. So in terms of triboelectric generators, that's the kind of research we're doing in terms of powering microelectronic devices and as well as harvesting energy from ocean waves.
Well, thank you so much for sharing some information today about how nanotechnology is being used both in the generation and storage of energy. And I want to thank you for taking your time to talk with us. Do you have any closing thoughts that you'd like to share with our listeners?
Thank you, Lisa. The only closing thought I have is that I would like to request the general public to closely read the papers and inform themselves better, in addition to reading news articles about nanotechnology.